Alright, here we have stage 1 of glycolysis. And the overall method of glycolysis follows this reaction up here. Glucose plus 2 phosphates plus 2 ADP plus 2 NAD plus yields 2 pyruvate molecules, which are both 3 carbon structures, 2 ATP, 2 NADH, 2 H pluses, and 2 H2O. And the goals of this stage 1 are to convert a glucose molecule into fructose 1,6 bisphosphate. And this whole stage 1 requires energy, more specifically 2 ATP. And the isomerization occurs because these 3 carbon molecules can only be metabolized. The body can't metabolize glucose as it is. So here we have step 1, our glucose molecule, and the first step is it undergoes a reaction with hexokinase and ATP and gets phosphorylated to glucose 6-phosphate. Hexokinase is an enzyme that induces a fit with the substrate glucose, and the interaction with the substrate forces water out and it increases specificity. So the next step we have here, glucose 6-phosphate, is also another important note, is glucose 6-phosphate is not recognized by transporters and is unstable, thus must be converted to fructose 6-phosphate and then cleaved into 3 carbon structures. So the next step, glucose 6-phosphate undergoes a reaction with phosphoglucoisomerase, and this to form fructose 6-phosphate. And this step is reversible because it's an isomerization reaction, and no energy is required in this step. Next, over here, we have fructose 6-phosphate reacts with phosphofructokinase and ATP to form fructose 1,6 bisphosphate, which is our final product. And this step is irreversible and rate limiting and also requires energy. And over here, we have the energy diagram for all of the steps in stage 1. And so we have glucose goes to glucose 6-phosphate as a result of ATP and hexokinase. And then this jump here is very large, which is why it's irreversible, compared to this step here, which is very small, the second step, which is reversible, the isomerization. And then lastly, this third step from fructose 6-phosphate to fructose 1,6 bisphosphate is irreversible, as you can see, this large jump here.
Cool. We're doing step 2, okay? Step 2 of glycolysis. So we left off and we last formed fructose 1,3 biphosphate, and the ultimate goal of step 2 here is we want to form 2 3-carbon molecules which are going to ultimately be metabolized in step 3. And this process of step 2 ensures that there is no cellular waste, and it is also rapid and reversible, and we'll talk more about that when we get over here. Also, I'd like to remind that this is the overall reaction. We're starting with glucose, and we're adding 2 phosphates, 2 ATP or ADP, and 2 NAD+, and we're ultimately receiving 2 pyruvate, 2 ATP, 2 NADH, 2 protons of hydrogen, and 2 waters. So that's just for fun. So yeah, we have our fructose 1,6 biphosphate, and I've drawn it out here in the furanose ring, and then I also redrew it in its open chain form so that way we can better visualize it for the reaction that's about to occur. So overall, this is what's occurring. We are starting with fructose 1,6 phosphate, and we're going to convert this into 2 different molecules. We get our glyceraldehyde 3-phosphate, and we also get dihydroxyacetone phosphate. So we get these 2 different molecules, but ultimately we want glyceraldehyde 3-phosphate. So these 2 molecules are interchangeable, and that requires a specific enzyme that we're going to talk about more. So here's our open chain form of fructose 1,6 bisphosphate. and we're going to cleave it here using aldolase, which is an enzyme which forms an aldol, and we get dihydroxyacetone phosphate. Notice the phosphate and then -2 charge, and we take this and we convert it down using triose phosphate isomerase into glyceraldehyde 3-phosphate. And but there's multiple steps going on. So we ultimately want to get to here. So we start here and we have to get down to glyceraldehyde 3-phosphate. Also, in a separate reaction, we are taking fructose 1,6-biphosphate and we're taking the other half of it and we're using aldolase again to just directly form glyceraldehyde 3-phosphate. And from here we're going to proceed into step 3, and it's going to become more apparent what this is important for. And then also, just for the sake of continuity, we redrew this delta G landscape. And so we have step 1 in the top. I kind of condensed it. You see our 2 rate limiting reactions using the kinases in the step 1, and then here I boxed step 2, where we take fructose 1,6-biphosphate and we use aldolase in this reaction to form glyceraldehyde 3-phosphate. And you can see, based on how small that little jump is that it's very quick and it's very reversible, which is important. And again, I want to stress that this process, the reason that we get 2 different molecules is because this is not symmetrical. We can't just rip it in half. It's not that easy. So we have to form this and then convert it to here. And we convert it to here using triose, so that way we reduce our waste, so that way we maximize how much glyceraldehyde 3-phosphate we can create and proceed with. So that's step 2.
So this is stage 3 of glycolysis, the harvesting phase. Just to recap, in step 1 of glycolysis, glucose is transformed into fructose 1,6-bisphosphate, and in step 2, fructose 1,6-bisphosphate is transformed into glyceraldehyde 3-phosphate. Our relevant enzymes for this reaction are dehydrogenases, which do redox reactions, kinases, which we have learned before, remove or add phosphate groups, mutases, which are similar to isomerases and move non-proton groups, so in this case it will be phosphates, and enolases, which remove water in order to form an enol product. So remember that from stage 2 we formed 2 of our glyceraldehyde 3-phosphates, so from everything here on is going to be 2. So we start off with a redox reaction. Glyceraldehyde 3-phosphate is oxidized by glyceraldehyde 3-phosphate dehydrogenase, allowing us to add a phosphate group onto the primary carbon. And because it's a coupled reaction, NAD plus gets reduced NADH and is then used in the electron transport chain. Once we form 1,3-bisphosphoglycerate, phosphoglycerate kinase is allowed to take away a phosphate group and form 3-phosphoglycerate, and in that process we form ATP. 3-phosphoglycerate, which is transformed into 2-phosphoglycerate by phosphoglycerate mutase. All we did is move a phospho group from carbon 3 to carbon 2, and this makes it easier to remove later on in a cycle. So 2-phosphoglycerate is then transformed into phosphoenolpyruvate by enolase, and this happens with water exiting the system. And this dehydration makes it easier for this the phosphate group to get removed, once again, as we said, with phosphoglycerate to form pyruvate. This is a really unstable molecule, so it's only a forward reaction. And so pyruvate kinase removes a phosphate group, transforming ADP into ATP, giving us energy, and pyruvate is formed. Pyruvate is the final product, and that can be used later on to form amino acids, fatty acids. It can go into the Krebs cycle to be used to form more energy, or into gluconeogenesis as well. This is the overall diagram for the reaction, these are our rate-limiting steps that we went over earlier. This is the one right here, phosphoenolpyruvate into pyruvate. And the overall delta G is negative 96 kilojoules per mole, making this an exergonic and favorable reaction. And that's glycolysis. Good?
4 shot?